So what we want to do now is we want to look at applying some of our newfound skills with speeds and accelerations, and we want to look at a simple example where we're standing on a building or an edge of a cliff, and what we want to do is we want to drop something, and let's say we just have our cliff is high enough up where we can run some experiments that we need to run. And what we want to think about now is how our object, when we let our object go, what's going to happen is our object is going to, initially when we're here, let's say our time equals 0, our location or position, x, equals 0, position. And what we want to do, and our speed here, our velocity v equals 0. And what we want to do is we want to think about what's going to happen to our ball as it begins to fall to the ground. Now the reason we look at this example is whenever you take something like your marker and I let it go and it drops, it's going to drop under the influence of gravity. And the acceleration of gravity A, is 10 meters per second squared. And it's a constant for the whole trip down. So gravity is the acceleration under which our object is going to fall. And so what we want to do is we want to look at some equations for how our object, our little ball, is going to fall in time. So what we can do is we had two equations that we kind of talked about. We said that velocity was the change in position, change in x, over a change in time. And we had that acceleration was our change in v over our change in time. Those were our two equations that we had talked about. So if we want to know the location of our ball, our x for the ball, when we look at this, let's say we want to say v equals x2 minus x1, location 2 minus location 1 over some delta t. And let's actually put in t2 minus t1. Well, when we look at this, we know our x1 is always going to be 0. And we know t1 is 0. So essentially, we can put zeros in here, and those go away. So when we look at our position is going to be x2 equals the velocity we have times our time. But this is where it's going to be a little bit weird. Because what's going to happen is when we look at our acceleration, A is going to equal v2 minus v1 over t2 minus t1. But we know that t1 is 0 and v1 is 0. So what we see is that our velocity is equal to our acceleration times our time. So what's happening, though, is our velocity here isn't a constant. So what we really need to do, since our velocity is constantly changing in time, our real position equation for free fall ends up becoming 1/2 a t squared. Because we have to make a substitution into our equation to account for the fact that our velocity is constantly changing in time because it's accelerating. And so our position this is for free fall. With free fall, our velocity is just our acceleration for the amount of time that it happens, and our position is essentially 1/2 the acceleration times the time times the time. So with our new equations, let's take a look at what happens in free fall. So our location, our position x2 is 1/2 a times 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 time. And our velocity is 1/2 a, our velocity is a times t. So let's say after 1 second, what happens? When t equals 1 second. Well, our velocity is equal to 10 times 1. Our velocity is moving, our ball is moving at 10 meters per second. Well, where's the ball relative to where we let it go? Our x is 1/2 of 10 times 1 times 1, and it's 5 meters below. So it's gone down 5 meters, and it's moving at 10 meters per second. What happens when t equals 2? Well, when t equals 2, the velocity is equal to 10 times 2, or now it's moving at 20 meters per second. So the velocity is going to keep going up by 10 meters every second. And what happens to our position? Well, our location is 1/2 of 10 times 2 times 2, or x is going to be 5 times 2 is 10, times 2 again is 20. So our ball, after 1 second, it was here. After 2 seconds, it's way down here. So every second that the ball travels, its velocity is going to be going up by 10. But the position, because the position goes with t times t, or t squared, it's going to be changing at a rate of t squared as a square instead of linear. So the velocity in free fall is linear, at increasing roughly at 10 meters per second, and the position is going up as t squared, and so it's not going to be linear. So when we look then, let's take one more look. Let's now go to t equals 3 seconds and see where we're at. So when t equals 3 seconds, v is going to be 10 times 3, or 30 meters per second, and our position is going to be 1/2 of 10 times 3 times 3. So it's 1/2 of 10 is 5, times 3 is 15, times 3, x is 45 meters. So we can see that there's not a linear increase, because after 1 second it was 5, after 2 seconds it's 20, after 3 seconds it's 45. So the position is increasing with t squared. But the velocity went from 10 to 20 to 30. So the velocity is increasing linearly with time, the position is not. And so the idea is you should be able to use these two equations so we can calculate how far or how fast something is in free fall. Now that's the one thing we need to make sure that we keep track of in our verbiage, is velocities tell us how fast something is moving. Positions tell us how far we went, right? So we don't say, I know in regular terms, a lot of times someone will ask you, well, how far away is that? And you say, oh, it takes about an hour. It's about an hour away. Well, an hour isn't a measure of distance. An hour is a measure of time. You would say that it's some distance away. How far is a measure of distance? So we just need to make sure that we clean up that verbiage. And remember that velocity is how fast. So we don't say, we don't want to confuse acceleration and velocity. The velocity depends on the acceleration. The acceleration tells you the rate at which your velocity changes. So don't confuse accelerations and velocities. Your velocity is how fast. The acceleration is how fast you're changing the velocity. So if your acceleration is constant, your velocity is increasing all the time. If your acceleration is 0, your velocity is fixed. You may have some high velocity, which means your position is then changing in time. But don't confuse, don't put the word acceleration in for velocity. Don't say, oh, it was accelerating very quickly, because usually we only have, when we're going to deal with problems, we don't have a varying acceleration. We have changing velocities because we have a constant acceleration. So when we drop something, the acceleration is fixed. It's 10 meters per second per second. That's causing our velocity to change. So our velocity changes because we have a constant acceleration. Our acceleration is not increasing. We don't have variable accelerations. We have fixed accelerations that cause our velocity to change. Now you can say our velocity is increasing rapidly because we have a fixed acceleration, but we don't say we were accelerating quickly, because that would imply that your acceleration is changing, and our acceleration doesn't change, our velocity changes. So that's just one of those verbiages just to make sure that you're using velocities and accelerations correctly. But this would be how we would look at a free fall problem.